Okay, thank you, Professor Cooper, for the previous talk, and thank you everyone for being back here now. Now we have Xenofon, who's a postdoc in Professor Cooper's lab, and he's an expert in machine learning and combinatorial data analysis and optimization, right?
Yeah.
So without further ado, let us hear what he has to tell us. Thank you very much.
Thank you, Michele. Hello, everybody. I'm really happy to be here. We were discussing about that quite a long time ago, and I would like to thank Isabel and Sami for inviting us over. Yes, so I'm a research coordinator in Andy's group, and I'm overseeing most of the AI activities in the group. Today, I'll try to list some of them, and hopefully I'll try to map some of them onto your interests as well, so we can hopefully have some fruitful discussions afterward, and see how we can both benefit from a potential collaboration. My slide, the title of my talk is going to be on human-informed AI for in-the-loop chemical discovery. I feel I have to sort of justify some of the terms. I will, in the long run, I will explain how I define human-informed AI, but I think I need to explain what chemical discovery is for computer scientists' point of view and what in-the-loop actually means. Well, okay. What it basically means for us is optimization, really. So we want to optimize a specific problem. And as Andy correctly pointed out, in most of the cases, we don't have an objective function. We don't have an analytic formulation of the objective. And instead, we have to do measurements. You want to measure how much hydrogen your new materials produce. You want to measure how successful a chemical reaction is based on the product yield. And you want to measure whether you have good performance as an organic solid state material, which is usually measured through optical devices. These are only a few of the examples, but this is usually the case. And that's the most obvious pitfall. Other implicit pitfalls are with respect to the underlying optimization landscape. And this is far away from convex optimization landscapes, but it's not only that. Most of the time, they're also non-continuous and high dimensional. So that leads us to a specific, very quite narrow subset of methods, which we call them sample-based, data-driven black box optimization methods. And in most of the cases, these are Bayesian approaches. That's with regards to the chemical discovery part. Now, the discovery loop, because of these peculiarities of the optimization problem, you have to do sample-based optimization, which means there has to be a loop where a chemist initially narrows down a chemical problem, and then using robots, algorithms, and experiments, they validate, they capture new samples, they update the model, and then discovery process goes further on. That was up until today, or at least the last few years, because things are changing rapidly in this discovery loop. As Andy very nicely illustrated earlier, there's a lot more complex chemistries that we can explore these days, and the old approaches, naive approaches, are not enough. And we need to inject knowledge, whether that is from the literature through LLMs, whether that is from human experiential knowledge by chemists, or even computational models, simulation models that can hopefully, smooth out these irregularities in the optimization landscape. And this is a very nice example of two different optimization landscapes in chemistry problems. As you can see, the rightmost one is a lot more challenging. Chemists in the area call it as if looking for needles in a haystack. You can see all the optimi are like very localized in a specific region, and taking into account that you have lots of combination and lots of high dimensionalities in the problem, it becomes very hard to locate optimum solutions using standard optimization methods. So what this area of research that we're trying to develop and apply in chemistry concerns is about smoothing out these irregularities in the space through external knowledge, so you can more accurately represent the space but also ways to focus on these fruitful regions based on human intuition or other assistive models in order to faster navigate these spaces. One of the initial early works that we did towards this direction, and this relates to a question previously about hyperparameter optimization, how are you able to measure that your initial parameters for your Gaussian process, for example, are the correct ones? Well, you simply cannot. You have to do assumptions. But what you can do is you can have assistive models, especially if they can estimate uncertainty, and combine two surrogate models in one in order to achieve a much more smoother and richer representation of the space. For example, you can see a very simple example of the original Ackley function and how a Gaussian process approximates or builds a response function on using a GP, and then how, if you combine a Gaussian process with a random forest model, helps mitigate these differences. And that, of course, initially is very hard to achieve, but as more data comes in, the model can have more extrapolation capacity. The easiest way that we managed to blend these two surrogate models was through the acquisition function. So basically, you design two equal analogous acquisition functions, and we did it through upper confidence bound, where we estimated uncertainty from a random forest model and combined the two as a linear combination in order to have a richer sampling strategy. But what was a lot more interesting for us is that then the human or the modeler had the option to choose which auxiliary model to use as well. And that could link to what type of problem you're solving. So what we try to do is we pick the chemistry problem where the relationship between the input and the output parameters were linear. And we try to use a linear model as an auxiliary model in this case, which showed a lot more improved performance compared to just using a random forest. So that initially gave us a hint that humans and modelers can have an active role in this modeling of the space. Then the next medium version was to try to broaden up this human involvement through hypotheses. Andy touched upon about it briefly, but I want to approach it from a purely explorative approach, and how these hypotheses basically look like in a computer science scenario. These are nothing more than essentially constraints in the space. The main problem with these constraints is you don't want them to bias your sets, you don't want them to be over restrictive, so you need to find ways. So these are kind of like soft constraints. And each constraint corresponds to an opinion from a user. So let's say that this chemist thinks that the optimum is here, right? And somebody who has less experience is trying to look towards the edge of the box. And we know that the optimum is in the center, for example, because this is like a top-down view of the Ackley function, right? So we wanted to make sure that we can have multiple of these opinions at the same time without each of them contradicting the other and without the optimizer being biased by them. So that was quite challenging to model. We used a Bayesian approach where we modeled these soft constraints as box constraints, and then we placed a single Gaussian process on each of them, while at the same time we maintained a global Gaussian process that overlooks the whole space. So what you're basically achieving by that is that you're sampling from these local GPs, and then those samples, those seeds that are promising, you just promote them to the global GP and include them in the whole search. So we formulated that in a bi-level optimization problem where the lower level concerns with the expert opinions and the global level is just the overall GP. And it seemed to work quite well in the majority of the cases where we were concerned that we didn't want to bias the space. That was our main priority. And this is an example on an Ackley function where you have three hypotheses. Obviously, the green bar is spot on, and the red one is like quite far away. But we try to have different types of hypotheses together to see if any of them cancel out, or how these opinions about the optimum location in the function affect the optimization overall. So you see that the green colored points in these three graphs are sampled from good hypotheses around the center, around the optimum. We named the orange one as weak because they weren't very good either. And then we named the red ones as quite poor. So what you can see is that like red choices here, I don't know if I'm covering the screen here, but red choices here being quite quickly abandoned by the optimizer. However, the gray points, which are points sampled from the main GP, are not affected and biased by them. So you see that green points continue to be sampled further on, but gray points actually are not affected by the red points. So you still manage to go to that optimum. It's just a case of whether you have more good opinions or more bad opinions. You're going to get to that point, but you're not going to be biased against it. So then we try to apply that to a more practical scenario. I don't remember whether, Andy, you showed that specific graph. I might be talking about it again. So it's a chemistry problem where you want to mix different chemicals to maximize the amount of hydrogen these produce. And it's a quite big combinatorial problem with lots of choices. What we try to do is we try to encode some, pre-code some initial hypotheses of chemists. I think we injected 9 hypotheses, correct me if I'm wrong here, Abdu. We injected 9 different hypotheses and we tried to design them with different expertise levels. So some of them were intentionally quite bad. Some of them were intentionally quite good, quite spot on actually. And then we compared this approach with the previous naive Bayesian optimization method that Andy was talking about, the Nature paper, the initial Nature paper with a robotic chemist. What is interesting is that even in the first iteration, you already gained 50 iterations. You have a 50 iteration speed up by just choosing expert opinions. And then all these colored points means that are points that are sampled from human opinions. The gray points are just sampled by the global GP. And you can see the role of these color points as stepping stones into further advancing the hydrogen output. So we thought that was quite interesting. And we wanted to further advance this into a more dynamic way. Andy correctly pointed out earlier that this was initially hard-coded as a Wormstadt case, but we didn't have the time then to have it in a more dynamic human feedback. And to be fair, that's not the only problem. It's you know, the other pitfalls in that case. It's very hard to find chemists like in a 20-hour clock to be able to dynamically inject hypotheses, right? So that's a practical consideration as well. Another thing is sometimes hypothesis generation and ideas generation can be limited. You just run out of ideas. So you definitely need something to give you some sort of feedback or some sort of inspiration. So we wanted to see whether language-based models could play that role, could give lucky hunches, you may call them informed guesses, other people call it like that, just to test how large language models could provide knowledge around chemistry. So what we did is we had this hybrid optimization framework where we had a Bayesian backbone, Bayesian optimization backbone, and then you have a separate LLM attached to it, which is monitoring the overall uncertainty of the Gaussian process. And when that drops down, or when you have a plateauing in the performance, the LLM kicks in and gives you ideas. So when you have very low uncertainty, there's no reason to resort to ideas because it seems that you're in the right path or that you're optimizing the target objective. But then when that actually starts to increase, it seems something is going wrong, or when you have plateauing performance, something is not right. And yeah, as we talked earlier, this was the GPT-4o mini. It was really interesting to see how information is extracted from LLMs. So we used previous data observations in the iteration in this continual loop, but also we used previous comments. So all this information, all these prompts were collected together and injected in each iteration inside the LLM, asking it to provide new insights. And then initially, before you start the whole experiment, you design something what is called like an experiment card, where you explain to the LLM what the problem is, what area is it on, what are your initial variables, and then you try to extract hypotheses out of it. And in this case, the hypotheses were not box constraints, as we were talking earlier. In HypeBio, they were more discretized version of these box constraints. They were isolated points in the space. In this case, I think we're using single points, but more points could be used. And how that process would start is by just asking the LLM, giving it an experiment card, what the problem is you're trying to optimize. Then the LLM would come up with some initial hypothesis. It would start running Bayesian optimization as normal. But then when the uncertainty was increasing or when the performance was plateauing, it would kickstart the LLM to suggest new points or sample. So you can think of it as a different acquisition function instead of the standard acquisition function we use, the expected improvement inside Bayesian optimization. And this is, we immediately tested that to the hydrogen production problem I spoke about earlier, but we tested to other examples as well. But it was really interesting to observe how these different regulatory quantities like the uncertainty or the trust score to the LLM change as the optimization progresses, because we had a safety lock as well in case the LLM was just spitting out random stuff, and you don't want that. So we were assessing these outcomes by the LLM using a trust score, and then after a few failed attempts from the LLM or a few bad guesses from the LLM, then you just stop using the LLM and revert back to the Bayesian optimizer. So it was really interesting to see how many times the Bayesian optimization, if you look at the green line there, how many times it was plateauing during the optimization. And then the red dots are like instances where the LLM was kicked in. It's really interesting to see how the trust score builds up, so it gets lower as we progress, which means the LLM is doing a very good job, which also translates into the maximum observed hydrogen production. And after some point, even the LLM could not change the course of things as well. So it was, go on.
If you take the points that the LLM suggested as part of the Bayesian optimization, or did you neglect them?
No, we were using the LLM as an acquisition function. So the LLM was suggesting where to sample next. Then we were doing exactly that. We were sampling these points, adding them back into the Gaussian process, and then updating it again.
With the Gaussian process?
Yes. Yes.
Okay.
Yes. Of course, we had another third case where if the uncertainty was not very high but not very low either, we're just using Bayesian optimization, but we're letting LLM observe the course of things in order to learn this from this in-context learning that people call it these days, in order to be able to extrapolate for future cases. That was very interesting. And what was more interesting for us to observe is that when you compare Bora, I don't know if I mentioned it, we call it Bora, this LLM approach, compared to HypeBio, Bora can achieve similar performances much earlier. But as Andy correctly pointed out, this is not entirely a fair comparison because the initial hypotheses were pre-hard coded into the problem initially and did not change at all. And this is to show that if you have a dynamic way of continual knowledge injection, it can help steer away from local minima potentially. What I'm really excited about is that we're actually now testing this in the lab. So we have, based on a recent Nature paper that we had from the group on a new automation combination of different robots, we're testing that and we're guiding that through Bora now. And we're testing it on a reaction generalization problem. And also we have a more scaled up version of this previous hydrogen production problem. We tested all these approaches, but now we're doing it in the lab in a much bigger space. And we're comparing 3 different approaches: naive Bayesian optimization, no knowledge injected, a bunch of actual chemists monitoring real time the experiments, injecting hypotheses, and just LLM-based hypothesis injection. So that would be the first ever real world analysis, if you may, to test how different types of knowledge injection can help discovery. I'm risking of repeating Andy's comment here. So we are in an age where we're less concerned about how to automate chemistry. We're already done that. I mean, Andy has already done that to a very great extent, and now we're more interested about what chemistry to automate. So we have all these automation platforms. Everything seems to be working with a very good precision. Now that we have a lot more powerful AI tools, we want to be able to be a bit more, adventurous with the type of chemistry we choose. Previously, in my previous slide, I talked about reaction generalization on the left side, and that was not the case before, like at least not before 2 or 3 years ago. People were usually optimizing reaction parameters for a single reaction. These days, people are trying to scale this up into optimizing reaction parameters for a bunch of different reactions, because this is a lot more useful to start with when you optimize chemistry problems. So with that in mind, we want to develop methods that can utilize as many information sources as possible, both at the input level, but also at the output level. And here I just differentiate from multi-fidelity approaches, because multi-fidelity automatically assumes that there is a hierarchical relationship between the different fidelities, which in chemistry at least is not apparent. And also we found in practice that it's quite hard to assume initial relationships between the different fidelities. Most multi-fidelity Bayesian optimization methods assume linear relationship between the different fidelities. And in our case, that is not apparent how to do that. But multi-information source discoveries is a bit more tailored around output sources of the same chemical experiment that are not directly an approximation of it, but closely related to that. They might not directly give you, let's say, a same output with some error, but it would give you a similar result that could hint to the right solution. So this is a very interesting area for us. And as Andy pointed out, we want to maximize all the different types of AI in order to contextualize Bayesian optimization with knowledge. I'm going to briefly give some examples of what we've tried so far. So with one of the active areas that we're working on is developing machine learning models. Mingao, who's here, has recently submitted a paper, and I think it's going to get out soon, in chemical science, where we developed a foundation model for a specific class of materials called organic crystals that works quite well across a universal type of property prediction. And when we designed that foundation model up, we had specific questions in mind and specific modeling ideas in order to be able to capture all the different properties and all the different crucial representation details. That was trained on a huge database of materials, around, was it 500,000? Yeah, well, yeah, something like that. And it was using multiple modalities, multiple different representations of materials, using graphs, using text, using images. And the results were amazing, at least for me. So comparing to standard machine learning approaches, we were able to outperform them by just fine-tuning with only 100 data points, which is with 100 different organic crystals. And this is very important for lab-based experiments, because in a single run, in a single loop, you're not going to get that many data points anyway. So if you're trying to, in each different problem that you're trying to solve, if you were to retrain your whole model from scratch, it would take ages. But this is where foundation models are very useful in lab-based chemistry. But that was not it. It was able to explain quite well where these predictions were coming from. And all these successes were observed across different properties as well. So we're moving towards a universality of prediction, a universality of space parameterization and contextualization. And we verified their explainability with actual physical models that physical chemists tested on them. So, yes. So these are regression tasks. Regression tasks. The main what? Yes. Oh yes. So yeah, I forgot to mention. So the main transformer architecture we used was BERT. It was like a language model, and then we just added modalities on that, graph modalities, uh, and vision modalities to transfer this knowledge from language to crystals. Yeah. So just forgot to mention that you can represent materials as text as well. So this is where this common transfer occurs. Another way that another area that we're really interested, as I mentioned before, was language models, large language models, and what we see as a next step, and GU has already started working on that, is extending these transformer models with combining them with lots of corpus information in order to build conceptualization for chemistry. Then what that we hope to have in a few months is to have an LLM that users and chemists can interact with and ask questions about what Andy was asking earlier before, like, is this material good? Is this dye going to be useful for this problem? And all these sort of questions. And quite a lot of recent papers have started to do similar stuff. And we had an interesting discussion with one of the leading companies in orbital materials actually are building something like that. So we want to further exploit this new trend of literature summarization into that transfer learning approach, where it's not based only on crystal properties, but also on textual information that links and builds different concepts in chemistry. I think GU has a much better slide on that. So I don't know if I'm gonna show these slides later in the networking event. And of course, we are very interested about generative methods as well. One of the early attempts at that is the very nice and interesting work by Milo, where he's trying to build crystals in a Lego style building approach, where you define an initial space where you want your crystal to live, and then you define how close the different molecules can be together. And then what you want from this approach is to find packings of different molecules in a box that are very close together, which then leads to other interesting properties like low energy, stability, and you get better chances to finding them in the lab actually. So how Milo is modeling that is with a method called entropic trust region, and relaxing that into the statistical manifold. Right? Correct me if I'm wrong. It's not my expertise. And then we have constraints about all the crystallographic symmetry groups. And what you essentially are trying to do is you're trying to optimize parameters of a distribution. And when you have a distribution of all the crystals that are very closely packed, when you have that manifold, then you can draw infinite different crystals out of it. So a few early preliminary results show that we can actually verify that these generative approaches generate crystals that actually exist or have been found to exist by sophisticated simulation tools. So how we envision to build that approach is to integrate all these capabilities into an optimization approach, where either that is hosted by an LLM agent or not. It gives the user the option to visualize different options, and then through preference-based optimization, you can weigh which ones you like, and then continue down that route. It's just a way of further contextualizing the search and weighing options for the chemist. We are also trying to find better ways to scale up multi-user interaction, multi-chemist interaction in experiments. And we have this interesting platform as a prototype built by Abdu here, where different chemists can log in and monitor the same experiment at the same time, inject hypotheses, and then all these hypotheses are aggregated and injected into the algorithm. We had a very interesting discussion with Michele earlier on how imprecise probability distributions can help into that modeling. Right now, we're doing it in a very crude deterministic way, but it will be really interesting to discuss how this can be modeled properly, because you get users with different expertise, and then you want to maintain a fair aggregation of knowledge as well, right? But we think that that is very interesting, not only from a research point of view, but also promoting global collaborations. Imagine that you have a lab based in Liverpool, and then you ask different experts from all over the world to contribute to the same global challenge. Last but not least, it's the topic that Andy briefly touched upon in his talk, is the data visualization part. As I explained in the beginning, we do things in the loop, in iterations, and it's very useful to have a global overview of the materials that you're discovering in each iteration and their interrelationships in a screen. That is very important, but is also at the same time quite challenging, because you want to build incremental embeddings while at the same time maintaining global view, right? So as new data points come in, they need to embed it into the previous snapshot of your visualization without, messing around with the global structure of your data points. And why we think that is very important, it's not only to give chemists intuition about what they're exploring and where they want to go, i.e., where to shift the focus of the Bayesian optimizer, but we also see that as an attempt at self-improving visualization through human input, like as a human in the loop data visualization, where humans actually change and direct the visualization algorithms, where how to visualize it a lot more precisely. And something that is not realized perhaps so much in the computer science community is that in chemistry, data visualization is not a static thing. So it's not, you don't have fixed data that you just want to plot them, identify patterns, and then extract conclusions. It's a vicious cycle, really. So you have to choose first which features you think are important, because in chemistry you have way different methods to measure features for one single molecule. You have different properties, you have different featureization approaches. Then you have to choose initially, hypothesize initial X features, reduce dimension, and then assess whether these patterns actually comply with your knowledge. And if not, you have to go back, choose other features, and do that in a closed loop thing. Which talking to many chemists is a very challenging task till this day. And existing visualization methods are not helping either. So all these different activities that we have or that we plan to have are capped by these open challenges that we encompass day to day. How can we fuse different sources of information, both at the input level, but also at the output level, in order to be able to contextualize even more the search, but also arrive to same conclusions much faster with less cost at the same time. Also, can we build upon the LLM reasoning? Can we have more theoretical underpinnings of the LLMs? Essentially, an LLM is now hard-coded in our existing algorithm, Bora, but can we have a more theoretical approach where, for example, an LLM is a planner and chooses how to switch from Bayesian optimization to LLM to maybe another model? Essentially, if you think about it, it's a partially observable Markov decision process, and nobody has looked at these theoretical underpinnings of LLM so far. We're really interesting to have robust and guaranteed performances for Bayesian optimization, which our method does not have at the moment. So it was actually one of the comments by the reviewers that we got. And the final bit again is this data visualization bit that is and has been missing all this time in the loop, which according to me and Andy is a very important component. Yeah, I'm slightly early, but I'd like to thank, first of all the guys who are here, Abdu, Mingao, Milo, GU, of course, Andy, and yeah, the Leverhulme Trust for funding my research and the whole Cooper group. Thank you for listening. I'm happy to answer any